Hello and welcome. This is SFU Math152, Calculus 2. My name is Brenda Davison. This is section 11.1, sequences. So we have spent the first probably 2/3 of this course talking about the definition of the integral, the definite and the indefinite integral, how to use the definite and indefinite integral to investigate certain types of things like area and arc length and volume. And we've also talked about how to evaluate integrals, to find the indefinite integral and to find definite integrals. And now we're going to do something that's related but actually quite a bit different. So it's sort of like we're now starting a whole new topic, sequences and series. So we're going to start out with a sequence. A sequence is simply a list of numbers. Okay, so we're going to have some notation and vocabulary surrounding this, but I want you to bear that always in mind. If I say a sequence, I just mean some sort of list of numbers. Okay, so here's the definition here. A sequence is a function whose domain is the set Z plus. So this is the set of, we use this notation to mean the set of positive integers. Okay, so that we've listed those there. So it is the numbers 1, 2, 3, 4, etc. Now we can have a function, which here we're calling s. So we have here a function. It says if the function is named s is such that it maps, we would say this, it maps the positive integers to some real number. So for each positive integer, the function produces some real number. Then the output, s of n, is usually written s sub n. Okay, and we can also write the whole sequence as the list of the outputs. Okay, sometimes the domain of a sequence may be taken to be the numbers 0, 1, 2, 3, 4. So this is the inclusion of 0, at which point we use this, the set of natural numbers. Okay, and then we would indicate that here. So basically there's an assumption that n starts at 1 unless we indicate otherwise. We can start at 0, we can in fact start at 2 or 3 or 4, whatever we want. If we don't put anything there, then we're assuming that it starts at 1. Okay, now we're going to just look at how we could, for example, define a sequence. So here's a sequence, cos of n pi, n equals 2 to infinity. What does this mean? This means the set of numbers that look like this. Cosine of 2 pi, that's when n equals 2. Cosine of 3 pi when n equals 3. Cosine of 4 pi when n equals 4, dot, dot, dot. Okay, those are equivalent representations of the same list of numbers. Now you can notice that if I were to make these calculations, I calculate what is the cos of 2 pi, what is the cos of 3 pi. This in fact is equal to these numbers right here, 1, minus 1, 1, minus 1, 1, dot, dot, dot. So I could write this, in fact, in what looks completely different. It would be like this, the set of numbers, which I compute this way, minus 1 to the n for n equals 2 to infinity. That's going to give me the same, I mean, it looks quite a bit different from this thing here, but this thing here and this thing here give me exactly the same sequence of numbers. This is a sequence of numbers right here. It is just a list of numbers. Okay, we also could write this in this way here. an, the nth number in the sequence, looks like this. That would also be a description of the sequence that we've done. Okay, so they can look a little bit different, but if the numbers in the sequence are the same, then it is the same sequence. That's A. Let's take a look at B. We are going to graph this sequence here. So I'm going to draw what this looks like. So what I'm going to do is just compute the first maybe 5 or 6 numbers in this sequence. So I'm going to do that here with the assumption that n starts here at 1, n equals 1 to infinity. This is assumed because it is not specified. So I can compute A1. A1 is going to be when n equals 1, so it's going to be 1 plus minus 1 to the 1 over 1, and that's 0. Then I calculate A2, that's when n is equal to 2. So I substitute in 2 for n, and I get here 3/2. Then A3, I substitute in n equals 3, and that is going to be 2/3. And so I just keep going through on these calculations. Why don't you just confirm by calculation that A4 is 5/4, A5 is 4/5, A6 is 7/6, and A7 is 6/7. So you can go through making the calculation for whichever values of n that you wish to, and then we can draw what this looks like. It looks like this. We have an axis here where we have n, and we have, in fact, I'm going to lower this down a bit because it never goes negative, so it's going to be easier for me to do it this way. N, okay, and then we're going to have here 1 and 2. So this is going to be n, and then this is going to be the function of n that we have indicated right here. It's not a continuous function. The function is, the domain of the function is only the integers. So when n is 1, a1 here, which is f of 1, is 0, and then when n is 2, we calculated that it's 3/2, like that. And then when n is 3, we calculated, I'm just going to put a dashed line here so see where that is, 2/3. And then when n is 4, we are at 5/4, and when n is 5, we're at 4/5. And when n is 6, what did we get for n is 6? We got 7/6. So we're a little bit closer here. And then when n is 7, so we can keep going like this. Okay, so that is 6/7. So that is a graph of the function. Okay, you do not connect the dots. The function is not defined, for example, at 1.5 or at root 2. It is only defined at the integers. It's a list of numbers. These numbers here do not have to be integers, and you can see they're not. But the domain, the values in the domain are always integers. So the function is defined only here on the integers. You can also see, I mean, you can see it from the picture and maybe from the examples, but we can also take the limit here. We could ask what is the limit as n goes to infinity of 1 plus minus 1 to the n over n. And when n gets very, very large, of course, this thing here in the denominator gets large. A minus 1 to the n is either plus or minus 1. So that stays basically in absolute value at 1. And then the denominator gets very, very large. So this thing here basically tends to 0. And so the limit here is 1. Okay, so we just did a limit, in fact. So now we're going to have a bit more of a definition of that. This is an informal definition of the limit of a sequence. So a sequence, there it is here. The sequence defined by whatever rule that is. How do you compute an? It has a limit L, and we write that the limit as n goes to infinity of an equals L, or an approaches L as n approaches infinity, if we can make the terms of an as close to L as we like by taking n sufficiently large. Okay, so if the limit exists, we say that, this is going to be an important word, if the limit exists, we say that the sequence converges, and otherwise it diverges. Okay, so we're going to get a little bit more formal definition right here. This is what I wrote here, epsilon n definition. So if you, in Calculus 1, you might have saw the epsilon delta definition of the limit. This is very similar. So what we're saying is a sequence has a limit L, and we can write that like we have here. If for every epsilon greater than 0, there exists corresponding n, such that the difference in absolute value between the sequence and the limit is less than epsilon whenever n is greater than capital N. Okay, that's the precise definition limit of a sequence. Okay, so let's just take a look at a couple of examples here. Is the sequence 2n divided by n plus 3 convergent or divergent? So just to make sure that we understand, what we're saying that is we have a list of numbers here whose rule we're going to compute in this manner. Okay, so for example, A1 would be 2 over 4. A2 would be 4 over 5. A3 would be 6 over 6. A4 would be 4 times 2 is 8, 8 sevenths. Let me think if I've done this right. A1, I'm putting in 1 for n. I get 2, yep, 4. A2, 4, 5. A3, 6 over 6. A4, 8 over 7. A5, just do a few more. A5, I would put in 5. I would get 10 over 7. And A6, I would put in 6. I would get 12 over, let's see, 6 plus 3 is 9, etc. Okay, so at least the first few numbers in this sequence look like this: 1/2, 4/5, 1, 8 sevenths, 10 sevenths. That something seems wrong. 7. When 4 plus 3 is 7, 5 plus 3 is 8. Fix that. 4, 5, 6, 7, 8, 9. Okay, that seems better. 10 over 8, which is 4/5, 5/4. And then 12/9, which I could reduce to by dividing by 3, 4/3. Okay, so we have some list of numbers here. That's what a sequence is, a list of numbers. And in this case, the list of numbers is given by this rule. We're asking what is we're asking, is it convergent or divergent? So we take the limit as n goes to infinity of 2n over n plus 3. That is equal to the limit as n goes to infinity of I'm dividing top and bottom by n plus 3 over n. And then as you take the limit here, you can see that this thing here will be going to 0 when n gets large, so the limit will be 2. You could also look at this, the ratio of the leading coefficients. They're both numerator and denominator, a polynomial of the same degree. So you can just take the ratio of the leading coefficients. It has a limit. That limit is finite. The sequence is convergent. Okay, so let's take a look at what we've identified here as a theorem. That is, if we have a sequence like this, where we identify f of n as an, where n is an integer, this function here, domain is the positive integers. What we do is we consider the sort of same function, but expanded to the real numbers. So we can say, if we have a function f of x, such that f of x equals n when x is an integer, and the limit, when we take the limit on f of x, we get L, then we'll get the same limit when we take n going to infinity on an. So what does that mean here? It means here, I'm just going to get a different color here, get the red because that's what it's in. So f of n are these numbers right here. Okay, this is f of n are these ones here. Okay, it's some rule that calculates these numbers right here. F of x is the whole thing. F of x is the whole pink line. That is the whole pink line. And you can see that f of x equals f of n when x is a positive integer. Okay, so then I can take the limit on f of x, and that will be the same as if I take the limit on f of n. Okay, if the limit becomes infinite, it means that for every positive integer m, there's some integer n such that when an will be bigger than m whenever n is greater than capital N. Okay, that means the sequence is divergent. This is a divergent sequence in a special way. There's two ways a sequence can be divergent. So let's just write this first. This is a divergent sequence. All right, and that means in this case, this one is divergent to infinity. And let's give an example of that. an equals n. And the limit as n goes to infinity of n is infinity. So this is a divergent sequence. It's a list of numbers such that when you keep going, the numbers just keep getting larger, 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 larger. Okay, there's that type of divergence. And just to make note of this, we're going to see this coming. This is different from oscillating divergence. Okay, when something oscillates, it doesn't grow arbitrarily large, but it also doesn't become closer and closer and closer to a particular value. Here are some facts about sequences. If we have two convergent sequences, so let's make clear note of what the hypotheses are. Our hypotheses here are that the sequence AN and the sequence BN are convergent and C is a constant. Then all these following rules apply. Okay, that if we take the limit on the sum of the sequences, that is the same as the sum of the individual limits. If we take the limit of a constant times a sequence, that is the same as the constant times the limit of the sequence. If we take the limit of a product, that is the same as the limit. If we take the limit of a product, that is the same as the product of the limits, etc. And so here's the division one. That's, of course, we have to exclude the case where the limit on Bn is 0. If we exponentiate, we can take the limit first and then exponentiate. P is a constant. If we take the limit on the absolute value of a sequence is 0, then the limit when you take the absolute value signs away is also 0. If we have 3 sequences such that Cn satisfies the condition that it's always between AN and BN for all n bigger than capital N, and if the two limits of AN and BN are L, then the limit on Cn is L. You should recognize this. It's a statement similar to what you've seen in Calculus 1. This is the squeeze theorem. And we will use this continuity condition sometimes here. If the limit is of an goes to L and and then we have a continuous function f, continuous at L, then the limit as n goes to infinity of f of an is f of L. Okay. These are some facts about sequences. Okay, let's take some examples. We're going to make use of a few of these facts as we're doing these examples. So here's 10a. Show that the sequence the nth root of n converges to 1. So we'll do that first. Okay, so what we're looking at here is the limit as n goes to infinity of the nth root of n. And that I could rewrite this with slightly different notation. That looks like this. Okay, and that is an indeterminate. To me, this looks like infinity to the 0, which is an indeterminate form. Okay, so maybe coming into your head at this point is, I may want to consider using L'Hopital's rule, but we have to be very careful. We can't use it directly because we can't take the derivative of this function here. Why? Because it's only defined on the integers, so it's not continuous. So we can't take the derivative on something that's not continuous. So we can't. We should just be cautious. We can't take the derivative. So we can't take the derivative directly. Okay, this function an, this is not continuous. Okay, so we save ourselves by saying consider the related function. which is continuous, which is this, f of x equals x to the 1 over x. So you can see what's happening here is that f of n is equal to f of x when x is a positive integer. So now this function here is now a function of a real variable x. This is continuous. So we are now able to use all our mechanisms of calculus. So then we're going to now ask, okay, let L be the limit as x goes to infinity of x to the 1 over x. It's indeterminate form. And so first thing I'm going to do is take the log of both sides. So I'm going to get the log of the limit is equal to the limit as x goes to infinity of the log on this side, which is 1 over x times log x. That's an indeterminate form like that. L'Hopital's rule must be indeterminate form 0 over 0 or infinity over infinity. So I just rewrite this thing here as this guy here, the limit as x goes to infinity of log x over x. That looks like this, infinity over infinity. So now I can employ L'Hopital's rule, and I will be in the habit of doing it like this so you can tell what I'm doing. That is going to be the log. The log of L is going to be the limit as x goes to infinity, and I'm going to take the derivative of the top and the derivative of the bottom. That is 1 over x over 1, and then I can see that that is 0. So now I know that the log of the limit is 0. That means the limit is e to the 0, which is 1. So then I'm going to write this out in very much in detail here, but this is what this is the thought process, because the limit as x goes to infinity of the x root of x is 1, and nth root of n, there's a better square root sign there, n is equal to the when n is a positive integer, then the limit as n goes to infinity of the nth root of n is 1. Okay, so be a bit careful. You can't just immediately start taking derivatives and use all the mechanisms you're used of unless you're thinking to yourself, okay, I have a discontinuous function only defined on the integers, so I need to set up a continuous function, use that, and then use the information on that to go back and get some information about my original function. All right, what was the second question? Is the sequence, so that was B. So now we're wondering, is this sequence convergent or divergent? This one here. Is it convergent or divergent? Let's just take a look at some of the values of this thing. If n is equal to 1, then we have the sine of pi by 2, and that is 1. And then when n is 2, we have the sine of pi, that is 0. And then when n is equal to 3, we have the sine of 3 pi by 2, and that is minus 1. And then when I get, oops, n equals to 4, I'll have the sine of 2 pi, and that is equal to 0. And you can see what's happening. It's going to go 1, 0, minus 1, 0, 1, 0, minus 1, 0. So it's just going oscillating. This is oscillating, so it's not growing arbitrarily large, but it never approaches a specific value. Never approaches a specific value. So is this divergent because it oscillates? Okay. Okay, so it's divergent sequence. All right, next couple of examples here. What about this sequence, cos n pi over n? Does that converge or diverge? I mean, so the numerator is going to go from 0, 0, 1, or minus 1, and the numerator is just going to keep getting larger and larger and larger. So I think it's fairly easy to see that the limit as n goes to infinity of cos n pi over n is 0. You could, if you wanted to be a little bit more formal, you could use the squeeze theorem. I recommend you write that out as an exercise. So you could stop the video right now and analyze this limit in terms of using the squeeze theorem. All right, B. For what values of R is this sequence convergent? Okay, so the things that we're talking about looks like this. A1 is R. This is the list of numbers. A2 is R squared. A3 is R cubed. A4 is R to the 4, etc. Okay, and then we're asking, well, we're going to see what is the limit as n goes to infinity of R to the n. And that limit is going to depend on the value of R. So let's just illuminate the cases that we need to break this into. Clearly, if R is bigger than 1, like for example, R was 5, you'd be having 5 squared, 5 cubed, 5 to the 4. That's just clearly getting larger and larger and larger. So this thing is infinite, so it diverges to infinity if R is greater than 1. So that's a diverge to infinity. All right, how about what happens if R is between 0 and 1? Like for an example, R could be a half. Then we would have a half squared, a half cubed, a half to the 4th. That's going to go down to 0. So this thing here is 0 if R is between 0 and 1. Okay, let's think. What have I not covered here? How about when R is 1? Then we have R equals 1 squared, 1 cubed, 1 to the 4. That just keeps staying to be 1, so that clearly converges to 1. So that's what I've had here. Sorry, I should have put it here. This is what I meant to put the first one. It converges to 1 if R is 1 because, I was right, because like in the shorthand form, because the limit as n goes to infinity of 1 to the n is equal to 1. Okay, what happens if R is between 0 and -1? Okay, so now it's negative. R is negative between 0 and -1. We already have the result here for the positive situation. So I claim here that this is 0 if R is greater than -1 or less than 0 because the limit as n goes to infinity of an equals 0 means the limit as n goes to infinity of an equals 0. And we already have this case sitting there, so therefore I can immediately claim this here. Okay, what happens? We didn't actually, I'm looking here, did we cover the case R equals 0? Let's see if R equals 0. Seems pretty obvious. You have 0, 0 squared, 0 cubed, whatever, so it's going to be 0. Okay, what else do we need to do? We need to do R equals to -1. What happens when R is equal to -1? Well, we have -1, 1, -1, 1. It's oscillating. So this diverges. Doesn't diverge to infinity, it just oscillates. And what happens if R is less than or equal to -1? Then you have a situation where you have this one here diverging, and so we're going to have this one here. This one here also diverges. Yeah. So it's like -5 or something like that. You have some of them are undefined, and then you have the other ones growing large. So it definitely doesn't converge. So it diverges. Okay, so we have this statement here then. R of n converges for these numbers. Oh, no. Okay, so just a bit of caution. These are not the same. Okay, let's That's that function there. Okay, a few more definitions. We have to get what we're doing. This just early days on the sequences, and then we're going to, of course, be looking at series, which are much more interesting than sequences. This is early days. A sequence just being a list of numbers, but we need the vocabulary, and we need to be able to speak clearly, and we need to understand how we can sometimes work with these things in a rigorous manner and not make mistakes. Okay, so here we've got a sequence here, a list of numbers, and we call it increasing under this condition. An is less than an plus 1 for all n greater than or equal to 1. Okay, so basically it has this condition here. The numbers keep getting bigger. It's called decreasing if the opposite thing happens, if an plus 1 is always less than an. Okay, so that's this statement here. Decreasing, increasing. If it's either one of those two, we call it monotonic. So it can be monotonically increasing or monotonically decreasing. If it oscillates up and down, it is not monotonic. Okay, so let us take a look at three sequences. Are they increasing, decreasing, or neither? We have a list of numbers. All we're asking is it increasing or decreasing? So the first thing you do is we know the rule for figuring out what is an. That's the rule. So we can just make a list, right? And see what's happening. And then we can be a little bit more rigorous once we get a sense of what's happening. So we can put in we can figure out what is a1, which is 1 plus 1 over 1. And then we can look at a2, which is 1 plus 1 over 2. And then we could look at a3, which is 1 plus 1 over 3. It looks to me to be decreasing. We started at 2. Then we were at 3/2, and then we're at 4/3, and you can see that, I mean, this fraction in some ways just keep getting smaller. The 1 is already always there, so this appears to be decreasing. So it is in fact decreasing, but I could then say, okay, is an plus 1 less than an for all n? So I can ask myself that question, and how can I answer that question? Well, let me think, what is an? What is n plus 1? That looks like this. 1 plus 1 over n plus 1. And I'm wondering, is that less than an, which is 1 plus 1 over n? So now I'm going to algebraically manipulate this and see if I come out with a true statement. If I do, then I could reverse that back up and say, yes, this is true. So let's just see how I would do that. I would add the fractions on both sides. So here I'm going to get n plus 1, n plus 2. I'm wondering, is that always less than n plus 1 over n? I'm going to multiply both sides by n. And I'm going to multiply both sides by n plus 1. So I'm going to get n times n plus 2. I'm wondering, is that less than n plus 1 squared? Then I can expand n squared plus 2n. And I'm wondering, is that less than n squared plus 2n plus 1? Then I can subtract n squared from both sides, subtract 2n from both sides, and ask, is 0 less than 1? Yes, 0 is less than 1. Therefore, this is true, this is true, this is true, this is true. Okay, so so this is decreasing. Decreasing. All right, do the same thing for B. We have a rule for calculating this sequence Bn. It looks like this: 1 minus 1 over n. So it's 1 minus 1. Yeah, when n is 1, 1 minus 1, I get 0. Then it's 1 minus a half. I get a half. 1 minus 2/3. Okay, let me just write out the sequence of numbers that I'm calculating in my head. 1 minus 1 over 1. That's the first one. 1 minus 1 over 2. 1 minus 1 over 3. 1 minus 1 over 4. 1 minus 1 over 4. 1 minus 1 over 5. 1 minus 1 over 6. Okay, looks to me to be increasing, right? So I'm going to then check. I'm basically now checking, is Bn plus 1 greater than Bn for all n? That's the question I've posed to myself. And I can simply make that calculation again. What is Bn? That looks like this. That is Bn plus 1. And what is Bn? 1 minus 1 over n. Okay, then I do a little bit of algebra on this, and I get n over n plus 1 greater than n minus 1 over n, and then I see n squared greater than n squared minus 1. That is always true. N squared is always bigger than n squared minus 1. I mean, that is 0 is greater than minus 1. So then that one is true and that one is true. So this is, in fact, as I set it up in the beginning, an increasing sequence. Okay, and then part C is neither. Okay, let's just take a look at why. You can see that right away. It's this thing here. That's what Cn is. It's neither, because you can see what happens. You're going to have C1 is equal to 0, C2 is equal to 1 plus a half, and then so it's increased, right? Between 1 and 2 it is increased, and then C3 is 1 minus a third. So going from C2 to C3 it's decreased. So you had it increase and then you had it decrease. So it's not going to be monotonically increasing or monotonically decreasing. You're done. It's neither. Okay, a bit more vocabulary. Again, let me just say, I don't know if you find it boring or not, but the vocabulary is key. Having the exact words to describe exactly what you're talking about and knowing clearly what you mean when you use the words is really a powerful tool. So try not to say, oh, it's those words, I'm not totally sure what that means, it's probably this. Try to avoid thinking like that and say to yourself, okay, if when I see a word and I'm not totally sure what it exactly means, then I'm going to I'll look it up and remind myself of the exact meaning. I'm going to do that as many times as I need to, so that then when I do see it, I know exactly what it means. Makes a huge difference. It takes a little bit of discipline, a little bit of hard work in the beginning, but you get all the time back many times over. It's totally worth it. Okay, so bounded above. What does it mean to be bounded above? It means that all of the numbers A in the sequence AN are less than or equal to some big number, some it's not necessarily a big number, but some number, big M, capital M. Okay, it's bounded below if you can find some number little m, such that little m is less than all of the numbers in the sequence. If it is bounded above and below, then it's a bounded sequence. Okay, it never goes out of what basically you're establishing is you've got a sequence, who knows what it looks like, but you've got some number here, capital M, and you've got some other number here, this is n, and this is an, and you've got some other number, little m here, and whatever the sequence is, doesn't matter what it looks like, it's defined on the integers. Okay, but it never escapes into these zones out here. That is a bounded sequence. It's bounded above by capital M, bounded below by little m. And then there's a theorem that's actually quite powerful, saying that if you can show that your sequence is bounded and it's monotonic, which means it's either increasing or decreasing, then it converges. You can sort of see why this has to be. It's bounded, so you can't, I mean, here it's bounded above, in this case, in this drawing, bounded above by capital M, and it's increasing. So think about what has to happen. It cannot get bigger than m because it's bounded above. It's increasing, which means every term gets bigger than the last one. So it has to reach some sort of a limit, because it can't keep increasing and not go above m if it doesn't reach some sort of a limit. So every bounded monotonic sequence is convergent. So we're going to spend a little bit of time on this last example. There's going to be maybe some new things happening here, and this is, I think, a challenging example. But pay attention to the details. Maybe go through this one. Listen to me talk about this one, and then maybe go back and try to get the idea and do it yourself. And then if you can do that, perfect. If you can't, then have another look at each step and the logic behind what I'm doing here. Okay, so we have a sequence. The first thing that happens is it's defined a little bit differently than we are used to in the previous example. So here it's defined recursively. Okay, that means that the n plus first number in the sequence is defined in terms of the nth one. So let's just see how to calculate these ones. We get told that the first one is the square root of 6. So we know that a1 is equal to the square root of 6, which for the record is approximately 2.449. And then how do we calculate A2? Well, A2, that is equal to the square root of 6 plus A1. This is what makes it a recursive. I have to know A1 in order to be able to calculate A2. I do know A1 because I just calculated it. And in fact, A1 is the square root of 6. So this becomes this here. Okay, and I can calculate what that number is too. That is 2.9068 approximately. Okay, then I go to calculate A3. Well, A3 is the square root of 6 plus A2, and A2 is this guy here. So I have 6 plus A2, which is the square root of 6 plus the square root of 6. You can see what happens. This sort of whole nested thing happening here. How about we notice that the limit here is, sorry, the approximate value here is 2.84. And then I'll just do one more. A4 is the square root of 6 plus A3. And that is the square root of 6 plus A3, which is the square root of 6 plus the square root of 6 plus the square root of 6. So I think it looks quite pretty. Good wallpaper. This is 2.9974. And then we're going to wonder in this investigation, really the primary purpose of the investigate is a little bit of a vague word here when we haven't much experience with this stuff, but what we're going to do really is to say, is there a limit? Okay, so first we're going to see, is it increasing or decreasing or neither? And so it looks here to be increasing, right? We've investigated 4 values and they appear to be increasing, and they in fact sort of appear to be getting close to 3. But we cannot just sort of claim that and move on, right? We have to be a little bit more careful than that. So we're going to ask, our first question is show it's increasing. So it looks to be increasing. So let us show it is increasing. Okay, which means that, what does that mean I need to show? That means I need to show that an plus 1 is greater than an for all n. This is not as easy to do in the previous examples because I don't have a formula for an that has n in it. Like the formula for an plus 1 has an in it. So it's a little bit more complicated. So I'm going to use a technique that you may not have seen before called mathematical induction. So I'm just going to, on the side here, just give a brief mathematical induction idea. The idea of mathematical induction, and this is, there's in the appendix of the Stewart textbook, there's a write-up on this. So if you not clear at this at all, and then you want a little bit more information, you could look in that appendix of the Stewart textbook, or you could of course Google mathematical induction. You'll find large numbers of examples and descriptions of how this works. But here's my description of how it works. This is a bit of an aside. The idea is we're trying to show that something is true for all n. Okay, so what we do is we show it to be true for the domino n equals 1. Okay, and we imagine these dominoes stacked up like this. We show it's true for n equals 1. And then what we do is we go along and we assume the thing is true here for the n equals kth domino. But we show that if it's true for n equals k, it means that it is true for n equals k plus 1. Okay, so what does that mean? I mean, it means if I show it's true for 1, and if I show that if the kth one is true, it forces the k plus first one to be true. It means that if the first one is true, it forces the second one to be true. And if the second one is true, it forces the third one to be true, etc. So that basically means that if I knock down this domino, all the rest of the dominoes will go like that and all be knocked down. And then that's what I want. That is showed they are all true. Let's see this in this example here. Okay, so we take a look at the base case. That is n equals to 1, and that would mean A2 greater than A1. This is true. We already calculated. I mean, this is 2.9068, and that is greater than 2.449. So it is true in the base case when n equals 1, A2 is bigger than A1. Okay, so now what we do is we assume it is true for n equals k. Okay, that means I'm making the assumption that this is bigger than this. Okay, now I can do whatever I want that's algebraically legal, and my attempt is to show that this forces AK plus 2 to be bigger than AK plus 1. So what I'm going to do is add 6 to both sides. Okay, then I'm going to take the square root of both sides. And then I'm going to look at this and say, hey, that is AK plus 2. And that is this here is AK plus 1. I'm done. Okay, now therefore it's true for all. True for, I'm done, all n. Because I've showed that 2 is bigger than 1. And this statement right here that I've showed means I can imagine putting in k equals 1. And that shows 3 is bigger than 2. And then I imagine putting in k is equal to 2. And that shows 4 is bigger than 3. And that gets them all. Okay, so that's done. I'm done. That is a proof by induction that that this is an increasing sequence. So this is that is the end of the proof, and that is this technique is proof by induction. All right, so I'm going to do exactly the same thing now. So now I've showed that it's increasing. Now what I want to do is show that it's bounded above and below, because then I can apply the monotonic, what was that theorem called? Sorry, I get the theorem, exact name that I used, the monotonic sequence theorem. So I've now showed that it's monotonic. It's increasing, in fact. Now I'm going to take a look at whether it's bounded. If it's bounded, then I know it converges and it has a limit via this theorem. Okay, so I've got the fact that it's monotonic. In fact, I know it's increasing. So I'm now wondering, part 2, is it bounded? Okay, so let us take a look. I mean, it is bounded below by 2. Okay, I mean, you can see that the first one, square root of 6, is bigger than 2, and it's increasing. So therefore, it's bounded below by 2. We don't have to do much about that. It's bounded below by 2. So now, how about bounded above? Is it bounded above? Okay, so I claim that is bounded above. My claim is yes, by 3. It's bounded above by 3. I picking 3. I can it looked to me like it's bounded. It's approaching 3. I could be wrong, but I'm making the claim that it's bounded above by 3, and I'm going to prove that. I'm going to do it again by an induction. So I'm going to state the base case. That is when n is equal to 1, and I know that a1 is less than 3 because I just simply calculated. Okay, tick, base case taken care of. Then I assume the kth case. Okay, so I assume that AK is less than 3. And now I'm going to do some algebra. And then I'm going to try, my attempt here is to show that AK plus 1 is also less than 3. Because then I will know A1 is less than 3, A2 is less than 3, A3 is less than 3, A4 is less than 3. And that means, of course, that it's bounded above by 3. Okay, so I now add 6 to both sides here. And then I take the square root on both sides. And then I recognize this here as AK plus 1, and then that is 3. So if AK is less than 3, then AK plus 1 is less than 3. A1 is less than 3, therefore A2 is less than 3. A2 is less than 3, therefore A4 is less than 3, and therefore I am done. bounded above by 3. Okay, so now I have a sequence which is increasing and bounded. Okay, so the sequence that I have, AN, is bounded and increasing, and monotonically increasing. Therefore, that implies it has a limit. Okay, the whole reason I'm doing this is because I can then make this statement. The limit as n goes to infinity of AN is equal to L. This thing actually exists. I can't do this and say that the limit, like assume the limit is equal to L. I mean, what if there is no limit? Then you've sort of assumed you have assumed into existence something that does not exist. So, but by doing this work above and using the monotonic sequence theorem, I have made absolutely sure there is a limit. Now I'm going to say, let that limit be L, and then I can tell you that the limit as n goes to infinity of AN plus 1 is equal to L. Okay, because I mean, as n gets big, it doesn't matter if you're doing the n plus first or the nth one. They're both going to be that same limit. N is going to infinity. So let's take this here. The limit as n goes to infinity of AN plus 1, and that's going to be equal to the limit as n goes to infinity of the square root of 6 plus AN, because that's what AN plus 1 is. So the limit is AN, this limit on this side is now going to be equal to this, the square root of 6 plus the limit as n goes to infinity on AN. Why am I allowed to do this? Because of the continuity of the square root function. This over here is L right here, and this is also L. So I basically now have a equation here that says L is equal to square root of 6 plus L. Now I can solve for L. L squared equals 6 plus L, and I get here L squared minus L plus 6 equals 0, and that gives me that L minus 3 times L plus 2 is equal to 0. The solution to that, which is reasonable for this problem, is L equals 3. So now I know that the limit as n goes to infinity of AN is 3. Okay, so that was a recursively defined sequence. We showed that it was increasing, we showed that it was bounded, and then we found its limit. That is by far the most difficult problem in this lecture. Okay, that is the end of our lecture on sequences. I will be back with our introduction to series, a really super fascinating topic. Bye-bye. Thank you.